So we're kicking off day 2 of our look at relativity by taking a look at some of the implications and the results of Einstein's realization that the speed of light is going to be the same for everybody. And the first piece we need to look at would be the Lorentz Transformations. Now this is coming back to the frame of reference that we were talking about. Again, we had that person sitting on a park bench. Sorry, let's see if we can get a circular head here. So we've got a person on a park bench, sitting stationary relative to the surface of the Earth. We've got a person in a car, moving to the right with speed v. So that's velocity of v meters per second to the right. Let's give our bench person some arms just for the sake of it. Now, when this car turns on its headlights, if the person on the bench says that light moves a distance delta x, well, if we use Newton's laws, a person in the car moving at speed v would say that the distance traveled would be the x distance traveled measured from the bench minus vt, because vt represents the speed of the car times the time elapsed. That's the distance the car has traveled since those headlights were turned on. And in Newton's understanding and with Newtonian mechanics, that's the complete set of transformations. The differences in distance side to side or up and down don't matter, and time is the same for everyone. But Einstein built the theory of relativity with two ideas. One was that the speed of light is the same for everyone, which again is an idea he came up with when he realized that the equation for the speed of light didn't have any variables in it that depend at all on the frame of reference of the observer. And his other idea was to throw out the idea of a preferred reference frame. So remember, Newton realized that somewhere out there would be a frame of reference that was better and more accurate than the rest. And he thought if you searched the heavens for something moving in that frame of reference, you'd find the Christian heaven. Well, Einstein was the one that said, no, what frame of reference is as good as any other? It's not that Einstein didn't believe in the Judeo-Christian heaven. He was proud of his Judaism. He just felt that the actual heaven was outside the scope of the universe and wouldn't be directly observed by anyone who was still living and a part of the universe. So Einstein was one of the people who came up with the way to correct the transformations. And I say one of them. The other was H.A. Lorentz. Now, as we mentioned before, when things first got out, and they first realized that there was a seeming paradox in electricity and magnetism with our two positively charged rods, which would either repel or attract depending on the speed of the observer, Lorentz was a grad student. Now, I said it was the young whippersnappers that were right. H.A. Lorentz was the least young grad student in his institution. He was 51 years old when he started his master's and started his graduate thesis. Now, when he did his thesis, he didn't have any particular investment in this. He was just playing devil's advocate. He needed to come up with some sort of calculation to show that, yeah, he knew what was going on. And he came up with the Lorentz transformations by saying, let's just assume for the moment that the problem is with Newton. And he resolved this paradox by finding a new way to transform our position coordinates. And he found, in order to resolve it completely, you had to have a different time. So for moving along the x direction, our y and z remain unchanged. But he found very different expressions for position. For the x, we had that x minus vt that we're familiar with. but that was divided by 1 minus v over c squared, where c is still the speed of light. And, interestingly, his time had a similar component. So he found that time would also depend on the position. But now, how do we turn a position into a time? We divide by a speed. We're not going to divide by v. We actually have a v over c squared term here to make the units work out. But these are the transformations Lorentz came up with just by playing devil's advocate and saying, let's make this electricity and magnetism, this paradox, just go away. How do we make that go away? And it wasn't completely unreasonable, because we had never had anything in the lab that came anywhere close to the speed of light. So this couldn't really be verified. And it wasn't until about 20 years later when Einstein said, well, the speed of light has to be invariant, so let's assume that there's no preferred reference frame. Let's assume that what we have here is fundamentally accurate, and let's see what transformations we get. So Einstein just took those two ideas he had. He had this one, and he had the idea that there's no preferred frame, at least no preferred reference frame. And he did his calculation saying, well, if we do that and also impose on it that when our speeds are very, very low, the transformations look very much like Newton's transformations, because otherwise we know it's not going to fit with the experiment because it's worked so well so far. Completely different set of assumptions, completely different approach, identical results. He also ended up with the Lorentz transformations. So that is something that made people go, wait a minute, there might be something to this. It would still be a long time before this was accepted. Because, as we're about to see as we explore these, we come up with some very strange ideas and things called paradoxes, like the twin paradox, and other ideas that are going to need to be resolved before you move on. We will continue that with part 2.